just pretend that this is now the x-axis. Y equals 8 is the x-axis. Okay? Well then, if y equals 8 is the x-axis, what is the real equation of this? And just think about rotating the upper region around this newly discovered x-axis, right? Then what is the equation of this line? If the original line was, it's a 2x squared shape, but it's flipped and moved 8 units up with respect to that, right? So it's 8 minus 2x squared. Agree with that? So the equation of this line with respect to the new x-axis is 8 minus 2x squared, right? Do you see that? And so what are we bounded by? We're bounded by this line. What is this line with respect to the newly discovered x-axis? 8, y equals 8, right? So 8 is my outer radius, and 8 minus 2x squared is my inner radius, right? So I'll just set it up like that. And I think your book teaches kind of like this. You subtract the axis of revolution minus the original function squared, that's your outer radius, and then minus the axis of revolution squared type of thing. But it's hard, maybe I'm wrong, but for me it was always hard to visualize that process. But if you just kind of, because relabel everything and then you're good. Just shift it all back to the original axis and then think how things will change. So you just do a vertical shift of the entire problem. Did that make sense? Did you like that? It's fun to think about. But this way, we'll just set it up as the volume is pi times the outer radius, which is just 8 squared, right? Radius squared, minus the inner radius, which is 8 minus 2x squared, dx, right? We're squaring the radii. And what are the limits? 0 to 8 or 0 to 2. We're doing the dx thing. So 0 to 2. X varies from 0 to 2. Okay? So whatever that equals to. We'll get that, right? It's a nice integral. So you can think of these problems like that. When they give you an alternative axis, either horizontal or vertical, just kind of shift everything with respect to the new axis. And then just, I think it's easy, I don't know. It's easier to me to visualize. So 64 minus 64 plus, what is it, 16, 32, 32x squared minus 4x to the 4th dx, right? So 64's cancel. And we get pi from 0 to 2, whatever that's left, 32x squared. I can just integrate it. So that's pi. So what is that? 32 over 3x cubed, right? Minus 4/5 x to the 5th from 0 to 2. Yeah, whatever that is. (896 15th pi), whatever. Not important at this point. You do the computation. All right.
Can you use the same method on x-axis?
Say it again.
Yes. Instead of having it be a with 0. he's asking if you rotated that, made that, and then like use the same method but on the x-axis. Rotate about the x-axis.
Well, but that's what I was doing really, right?
You just made a new x-axis.
Yeah, I just called.
Shifted his equation.
So this is what I did. I rotated kind of. This is the x-axis now. So we started with this shape, and we rotated around the 8 line, right? But then I said, well, let that be x-axis, really. So basically, what I'm doing is, I'm taking this shape. It's going to be hard for me to grab that shape. No, I cannot grab that shape for whatever reason. Here we go. No. Anyways, so I'm just taking this shape. You can think of it as taking this shape and dropping it down to the x-axis and rotating it. Is that what you're asking? Yeah. So basically, I call the axis of rotation my x-axis, and then I just changed. I relabeled my function so it satisfies the same kind of picture. Yeah. Let's do a fun one.
Can you roll show us a second?
Up or down?
I'll go on this one. Yeah, see.
Oh boy, this is too much fun. Are we ready to have some fun?
I want to ask you a question.
Go ahead.
If you just took that form and rather than rotate it around y equals, in this case, y equals 8, could you get the same answer rotating it around the x-axis?
Well, the,
Just
no, I mean like
straight away.
just as it was drawn and just rotate around the x.
Right.
No, you'll get some.
The same answer?
I don't think so. You'll get something different. You'll get this type of a shape, right?
Right.
If you rotate it around the x, you'll get kind of. Oops.
Well, but I mean, that's the same, it's not gonna be the same answer because it's a different equation. But it's gonna be equal to the same volume.
I don't think so. Because look, if you just take this shape as it was written, was that what you were asking? You rotate around the x, you'll get kind of like that type of a deal, right?
Right.
But the thing that we're getting kind of a that thing. That's what we're getting.
But when it's equal,
I don't think so.
slice that right down the middle, and then the bottom.
Well, let's do that. Let's just out of curiosity, let's just take this thing as it is and just rotate it around the edge, right? What do we get? It is pi. So that's just what? I mean, what are we doing really? Yeah, it's 2x squared.
So your outer radius is gonna be 8 still.
No. The 8 will come for free from the revolution, from the limits of integration. Because it has nothing to do with 8 right now. I don't even have a region between. Yeah, I'm just going under the curve 2x squared. This is a straight up rotation from 0 to 2. So when I plug in 2, it does get to 8, right? So if we just compute that, yeah, we're not even, right? We're not getting, what is this? This is 4x squared dx from 0 to 2, so it's 4x to the 4th. So we're just getting this part, right? There's a whole other chunk to it.
No, you don't have the,
Well, I mean, just by observation, compare this integral with that integral. I mean, they're not the same, right?
well, are they not
What?
the same?
Well, if they are the same, then
Yeah, 4/5 not the other one, so you're 4.
well, I mean, just
So you have
algebraically,
4/5, you're exactly right.
is this function just from algebra same as that function? No, so therefore the integrals are not the same, right? Can you say that? Well, you cannot say that, because then you can have different functions that contain the same area. All right, if I keep computing, then it's pi 4/5 x to the fifth from 0 to 2, right? So we can actually compute that. So you'll get 32 times 4, 128. So it's 128 pi over 5, and we got 896 pi over 15. These are the two different.
So that they should be.
Yes, they are. Why not? If you're saying if I took this region, no, you'll just get something else. Well, there's same shapes, they're not.
But they should be.
Why?
There's something we're missing here on the equation, because
No, we're good on the equation, I'm pretty sure. It's just different shapes.
well, because you're just doing an integration, you're just doing an integral of the shape. We're missing the line x equals 2.
No, we're not. It's here.
Just because of limit.
Yeah, that's what stops it. We're missing the line y equals 8, but when you do the bottom shape around the x, we don't need the y equals 8 because x equals 2 will block it at 8 anyways. So you just wrote, it's area under the curve. I,
I mean, the y-axis might have the same as if you rotate it around the x-axis.
I mean, your radius of rotation is different. Then by this argument, it no longer matters if I still block it by x equals 2, but instead of rotating around the 8, I'll rotate around the 10. And I'll set up this integral the other way. It's going to be the same integral, because x equals 2 will block it at 8. Now, when we rotate around the 8, you do have a ball that actually does not have a hole in the bottom. If I rotate around the 10, it will have actually a hole in the middle. But if I stretch the radius, it will change your cross sections are the same, but the radius is different. We're actually going to have a theorem later on. Like, you know how to find the volume of a donut? The cute way? There's a hard way and there's a cute way. I mean, the hard way, you think, okay, the cross section is a circle, so you have a function kind of like a circle, right? And then you rotate it around the radius. Yeah, you can do it like that. Or there is a theorem called the Pappus theorem, that it's really the area of a cross section times 2 pi radius. You just multiply it by circumference, and you'll just get, so basically it's a function of how far, how big is the donut, right? And the radius will be the center of the circle, from the center of the donut to the center of the circle. Basically, we're going to talk about the concept called center of mass. So we'll assume that the donut is uniformly baked. So each cross section, the center of mass is in the middle. So you just take the center of mass and you rotate. So I can take actually any region, any blob, and I'll say here's the center of mass or whatever, and the area is 2, and then just rotate it with the radius of 4. Then you just do like a distance from there to there. So that's 4. What was I saying? Was that the radius? Well, anyway, so we'll talk about this a little later, maybe next week. But the cross section is almost irrelevant at this point. It's not the function of the cross section, but the function of like radius and all those types of things. Yeah. Right. Let's do the fun one. I want us to find the volume of this shape. Find the volume of, if I can draw that. Can I draw that? Okay, no, it's not. So let me do it like that. Oops. So it's kind of like a pyramid with the top cut off. What is it called? Really? That's not fun. I think it's called like a, I don't know, like a frustrum or frustrum or frustrum. A word like that. Frustrum. I have it in my notes. Let me see how you spell that. Oh, there's another R. Frustrum. And there's no R here. I had an R escaping. Now we're going to have a square base. So base, base. So this is the B, this is the A, you know, and this is the H, the height. What? Yeah, is it? It is now. Okay. We'll define it like that. So I want to find the volume of that shape. Okay? How can we do that with everything that we kind of talked about? We're not rotating anything. We just have a geometrical object. Well, maybe, but I want to derive that. I don't know what the formula is, because the formula is well known. It's not nothing new, but I want to see what we can come up with that.
So you would do the average of A plus B times H multiplied by B.
Again, you'd give me the formula. How do you derive that formula? I don't know. How do you convince me that that's the volume then? I'm not saying that's true or wrong, but
Well, you can just find the area of the front shape.
you mean like the side
No,
of the, what do you mean the first trapezoid? You mean like that one? But remember that one is it's slanted, right?
Is it?
Right, it's like that. It's a pyramid. Well, it's picture a pyramid cut a top off. Maybe it's not a good. This is my slanting, right? It's slanted. I'm not good at three-dimensional projections.
Could it be surface area of the trapezoid and then just multiply it by B?
I don't think so. I don't know. Could be, but again, you just give me like geometrical formulas. I want you to derive those. Maybe they logically make sense. I don't know. I'm not saying that your formula is wrong. I want to know why that formula is true. What we've been doing so far. Yeah, but what is an integral? Well, yeah, but yeah, even the sum of what? Of things that we can easily find, right? So we're going to be slicing and dicing this thing. The question is, which way you're going to slice it so you get a consistent type of shape. So well, you'd have two options. You either slice it like this or you slice it like that. Which slices will produce, because that will make it easier life. The horizontal, right? Every time you slice it horizontal, you get a little frustrum, right? And the little frustrum is kind of like a rectangular box. This is our assumption, that we're no longer going to care about the slantiness of the walls. We're just going to assume we're just going to slice them. We're going to make a little square base rectangles, right? We're just going to slice them like that, and then we're eventually going to add them up.
So you can assume that there's pretty much no height for 50%.
There is height. Height is h.
That's delta H is what you're looking at.
Yeah. Yeah, so you'll be like a little delta h, but if we put it on the axis, it'll be like delta y in this case, right? Yeah. So yeah, so the h equals the length of the side, basically, because you're assuming that, you know. Just like with rectangles, you don't care about the curves, you assume it's a rectangle. The same thing here, so we're going to have a bunch of these little guys, right? Now, so A would be the length of the of that. So this is the A and this is the B. And we're slicing somewhere in between.
So it's square, right? Square, square.
Yeah, square, square. All right, so we need to somehow, so whatever this side is, right? So the volume is that side squared times whatever this height is, right? Times the height. That would be the volume of each of those things, right? Is that right? We just have to put some calculus labels on that, right? Now, so to make things prettier, let's kind of pretend that we do have a three-dimensional set of x's and kind of poke that thing with the y-axis right through the middle, so it, well, the z-axis rather, and then it just lands on the xy plane. We're just gonna look at this just from, basically I just want to look at it like, okay, forget everything I just said about the x's. Just kind of plummet it on the plane and then look sideways, so you just see a parabola, trapezoid, right? So this is right there in the middle. What are the coordinates of this point and that point? Yeah, so that's b over 2, negative b over 2, right? Right? Now, what would be the x coordinates of those points? So it's negative a over 2. I'll leave the y for an a over 2. What will be the y value? Well, it's not a. H, right? The y is the height. So y is the h. So h, right? Okay? Now, we took a slice through this. But yeah, but y equals h, as you guys pointed out. So we took a slice. So I really want to know the value, the x values of these 2 points, right? Well, how can I find them? Yeah, find the slope, because these are the 2 lines, right? These are the 2 lines. So I can find the equation of each line. Just take one line, right? We'll only need one. I can find the equation of a line, and then I can find the x or whatever the y coordinates. Is that right? And then what we're going to do, when we figure out the volume of each one of those rectangles, yeah, that's how we're going to do that. It's going to be a mess. Oh boy, so much fun. I don't know. No, we're just going to add them all together, right? Yeah, I want to. So let me just make sure. Okay, so let's see. So let's find the equation of this line. I want to find the equation of a line between 2 points, a over 2 comma h, and what is it, b over 2 comma 0. So slope is h, right, change in y, over change in x, so it's what? A over 2 minus b over 2, right? No, b over 2 minus a over 2, rather. That would be better, right? B minus a. I have my order messed up. So it's b over 2 minus a over 2. So that's h over b minus a over 2, like that, the same denominator already. You flip it over, so it's 2h over b minus a. What? Is that okay? All right, so that's the slope. So we can find the equation of that line, right? Equation of a line is y minus, what would be an easier point to pick? Maybe that one, because it has 0 in it already. So y minus 0. So y equals the slope, 2h over b minus a times x minus the x value, b over 2, right? So it's y minus y1 equals mx minus x1. Y1 is 0, so just y. So y equals, it is a minus b, right? That's what I wrote originally. And then I changed it for whatever reason. Yeah, so yeah, I'm doing this wrong. I'm going to get the negative results then. Am I right? Are you right? You're right. How do I fix it? Yeah. Yeah, so right, or if I just flip them, if I go, so which will flip this? Will just be a minus b. Anyway, so I just put negative h. So negative or flip this 2h over a minus b. This is the minor algebra errors. Yeah, you just have you got a positive slope instead of a negative slope. Who cares? Modularly speaking, they are the same. What? Okay. Is this better? You're right. Yes, thank you. I think that's better. Yeah, I thought so originally. I don't know why I changed it. So this is 2h over a minus bx minus, what's going to happen? 2's will cancel, right? When you multiply this by that. 2's will cancel, and what do we have? We'll have bh over a minus b, right? I believe I've deviated from my notes dramatically. I didn't know if I had to go that far, but I mean, what are we trying to do? We're trying to solve for x. We're trying to find this x value. So maybe there's an easier way of doing that. I mean, yeah, we got the equation of a line, but then I have to solve for x, right? It'll be easier if I solve for x from here without distributing. Do you agree with that? Because I mean, here I can just divide by the reciprocal. So if I just solve for x from here, so we'll get y times a minus b over 2h equals x minus b over 2, right? And then add b over 2. So x equals y times a minus b over 2h plus b over 2. That's the x value. Is that right? Yeah. This is the x value. Then what is the length of this whole side? So it's 2 that, right? So when I go back to my pretty picture over there, because this length was 2x, right? Because we just, with respect to the x's, when we put it in the middle, it's 2x. And we found x to be that, right? So just times that by 2. So if x equals this, then 2x is times it by 2. So 2 cancels here. So I'll write it as a minus b over h times y. And then 2 cancels there, plus b. This is the length of a side, right? And I have 2 of those sides. So for the volume, I need to square that, right? So then the volume is whatever this thing is, a minus b over hy plus b quantity squared, right? Times, what was the height of each one of those? What is the height? Well, delta y, right? If we put it on the y-axis. I mean, y will range from 0 to h. So times delta y. So this is the volume of each one of those little boxes, provided values of a, b, and h. Now, we're just going to add them all up, right? So we're going to take the integral of this thing right? And the y ranges from 0 to h. Woo! So this is fun. How do you integrate that? I mean, it's basically it's a linear function squared, right? Everything else is a constant. I'm gonna kind of use up this instead of expanding it, because it's gonna get really messy if I expand it, right? I know the integral of a square is going to be what? A cube, right? A minus b over hy plus b is going to be cubed, right? And then I need to divide it by the slope, right? Think about this. If I take the derivative, I'm also going to need a 3. So I need to definitely divide by a 3 because of the 3, right? And I'm also going to have a derivative. A minus b, h will come out. So I need to multiply it by a minus b over h. So everything cancels when I take the derivative, right? So if I write it in a more humane terms, what do we have? We have, so this whole denominator is what? It is, if I flip it to put it up front, it's h on the top over 3 times a minus b. Is that right? If you just flip everything, and then it's a minus b over h times y plus b cubed, valued from 0 to h. All right, let's plug it in. Am I correct? I think so. Yeah, close enough. Yeah, it is right. Are you okay how I integrated that? I needed a 3 because of the 3, and then I needed the slope, so it cancels the slope if I take a derivative. So when you plug in the h, you'll get h over 3a minus b times a minus b over h times h plus b cubed, right? Minus, we'll just keep that constant on the outside. Minus, when you plug in a 0, you'll just get what? B cubed. It's hard to see. Let me write it because it's messing with that. This is where we're at. Sorry. Let me copy it over here. 3 times a minus b times, what I have there is a minus b over h times h plus b, quantity cubed, minus b cubed. This is h, and that's a b. Is that what you're asking? Okay. So we can simplify this, right? H and h cancel. So we have the front times, what is left? So, yeah, it's a minus b plus b, b's cancel, right? So it's a cubed minus b cubed. And this is a minus b as well, right? So I can do some factoring and reducing. Can I? I can factor the difference of cubes. And the difference of cubes factors into a minus b times a squared plus ab plus b squared. So these two cancel. So it's h over 3 times all that. Is that right? Yes. So that's the volume of a frustum. Very frostomy type of problem, right? Well, it's definitely on the homework. Well, this idea, maybe not this messy, but the same idea that you can slice them and add them together. Now, here's an experiment that I want us to perform. Let A equals B. If A equals B, what do you get? Yeah, you get like a square base rectangular box, right? Well, if A equals B and I put it in there, it's h over 3, and then it's a squared plus a times a plus a squared, right? If A equals B, which is h over 3 times 3a squared, right? Which is what? H, it's the area of the base, a squared times the height. Good. We got the volume of a, well, not a cube. Because it's just as a square base, but the height varies, right? If h equals a, then we're definitely going to get a cube, a cubed. H could be anything. Now, what if we let a equals 0? If a equals 0, what do we get? No, but I mean like the shape. What kind of shape do we get if a is 0? So we just get a pyramid, right? If a is 0, then all those lines will converge. So if a equals 0, what do we have left? If a is 0, it's a b squared h over 3, right? Which is the volume of a square base pyramid. So this is volume of a pyramid. This is the volume of a square box, square base box. And this would be the general formula. Fun stuff. Okay. Let me. Well, I'm not done. I got more. So, anyways, I'm sure you got questions. This one is a messy, but But again, the idea is on your homework you'll have a problem. It's going to be a cute problem. I think it's on your homework. I haven't posted it yet. Let's say you have a tower, square base tower, whatever, consistent tower of height h, right? So here's some height h. And then you have the same exact base, only it's kind of like this. But, okay, not like that. Same height, so we have the same height, only it is tilted, right? So you have either it's stacked like this or it's stacked tilted, but it gets to the same height. So the question is going to be, what's going on with the volumes? Are the volumes going to be this way, that way, or that way? First one, that one is less. That one is bigger. One on the right is bigger. One on the right smaller. So you were talking about psychology earlier today, right? So there's this, the stages in human development. You go from 0 to 2, from 2 to 7, and then 7 to like 11, and then you grow up. That deal. So they actually perform experiments on kids that are like from 2 to, well, maybe not 7, but in that region. It's a famous experiment from like early century. You take 2 identical glasses and you fill them with water to the same height, and you present it to a child, go, which one has more water, or are they equal? And the child goes, well, they're equal. And then you take a skinny tall glass, and then you take, okay, now check this out. You pick up one of the glasses, and you pour the water into the skinny tall glass, so clearly the water level is now above from the other glass, and you go, which one has more water, or are they equal? And the child goes, well, the tall glass has more water. Because, I mean, look at that, it's more water. Then you ask a person who's like 10, they're like, well, come on, they're equal, because you just, I mean, I saw you do that, the same amount of water. So it's kind of, it's true, it's kind of fun. But this is the, so let me ask you this question. Pretend you have a deck of cards, right? And you just stacked normally. It has a volume, right? Now you just kind of push them so they slide over. It maintains the height. Is the volume going to be the same, or is it going to increase the volume? It's going to be the same, right? I mean, it's the sum of volumes of each card. So the volumes will be the same, because you'll do the same concept. You'll take the cross sections, they're all going to be rectangular boxes, and you'll just add them from 0 to h. So you'll have the sum of the same shapes from 0 to h. So the integrals will come out equal when you actually do this on your homework. But that's the same concept that, like we did with the first one. It's not going to get all mathematically, insane. Like by the way, it's an algebra problem. I can totally put it on algebra final. Set up the volume of the first term. I mean, without integration. I mean, just set the original thing up. But I mean, that's kind of cute, right? It doesn't matter, right? You tilt it. If you maintain the height stays the same. Yeah, I don't know if I'm entirely following you. I want to do one more thing. I want to rotate another. We'll just do one more rotation. Let's rotate y equals 2x squared minus x cubed and y equals 0. Rotate around y-axis. So, even if I factor this a little bit, right? So it will help me to maybe sketch a better graph. So I have a cubic function, right? It will have intercepts at 0 and 2, and it'll be like that type of a thingy. And we're bounding it by y equals 0 in that graph, so here's that. And we're rotating around the y, right? So we're getting, this is the rotation. So you're getting kind of like a wavy thingy, right? So we were rotating so far. When we rotate around the y-axis, we would slice it along the y-axis, right? So now, if you slice it this way, do you see a big problem with that? Because you need the outer radius, you need the inner radius, but both of those curves are defined by this function of x. So I really need to almost solve for x in terms of y, first of all. So good luck with that, right? Can you do that? I don't think it's possible to solve for x here in terms of y. And then you have to split it, right? Do you have to split it? No, you actually don't. You're always going to be between, yeah, you do. You kind of, between this curve, you have to do it as a 2 different curves, right? Kind of. Well, so long story short, it's impossible. You cannot do that. You cannot solve for x here. That's, the first thing you need to do. So doing our disk method is not possible in this case. We cannot just slice it, get a bunch of washers. So, but if we just continue with that logic, if slicing along the y-axis will not work, therefore, we should do what? slice it along the x-axis, right? Well, now what I'm getting is now, when I slice along the x-axis, here's my slice, right? Well, what happens to that strip? That strip gets rotated, right? So what am I getting? What kind of shape am I getting if I rotate that strip around the y-axis? Well, I'm getting like a can, right? Like an empty, hollow can. All I get is the walls, right? I'm getting what we call it a cylindrical shell, right? This is what I'm getting. These walls are thin. That's what we're going to make thin, right? These walls are delta x, right? Because that's the slice. That's the delta x, and it will define the thickness of the wall, right? What is the height of this cylinder? Just again, look at the strip. Where does the height of that strip comes from? F of x, right? That's your y value, f of x. So this is y equals f of x, right? Now, how do you find, first of all, do you know how to find the volume of this shape, geometrically speaking? Just the way we derive the formula for this shape, we're gonna cut it, and we're gonna bend it and flatten it out. So what do you get? If you just picture that, cutting this thing open and then flattening on a table, what are you gonna end up with? You're gonna get a rectangle, right? If you cut it and flatten it out, you're gonna get this thing, right? So the height of this is still delta x. H is delta x. This, the sides, is still your f of x, right? But then the length of this rectangle, because the volume of the rectangle is length times width times height. Well, the length of the rectangle is the circumference of this thingy, right? If you find the circumference of that circle, that's the length, and the circumference is 2 pi r, right? Well, what is the radius? This is the radius, right? Radius of rotation. Well, the radius is whatever the x is, right? Whatever the partition you choose, whatever the x value there, that's your radius of rotation. R equals x right now. You see that? Because, whatever this x is, r equals x, so it's 2 pi x. So the volume of this thing is 2 pi x times f of x delta x. So it's x times a function times 2 pi dx whatever delta x. So therefore, the whole thing, you'll just integrate from, whatever, a to b, and then it's 2 pi x f of x dx. So this is called the method of cylindrical shells, and it has the opposite variable. If you rotate around the y, you'll integrate with respect to x. If you rotate around the x, you'll integrate with respect to y. So we need two methods, because sometimes you do have functions y in terms of x, but sometimes it's impossible to get y in terms of x. So you're trying to get x in terms of y, and you integrate the other way. So this would be, so let me just write it down more officially. So cylindrical shells. Yeah, I think so. So if you rotation y-axis, then your volume is the 2 pi integral from a to b x f of x dx. So that's what you need to remember. You have the opposite variable. You rotate around the y, you integrate with respect to x. And if you rotate the x-axis, v equals 2 pi integral from whatever c to d y g of y dy, whatever the names and all labels are.
No, A and B is going to be like the outsides of the...
Well, whatever your variable ranges from. So in our case, if I try to do this function, it's just going to go from 0 to 2, right? Because again, I'm just thinking about all the different slices I'm going to take. So it'll range from 0 to 2. So the radius of each rotation is going to be from 0 to 2. So I can actually do this volume using this method now, right? Because then all I need, my function is 2x squared minus x cubed. It gets really, weird by the end of the day. So the volume is 2 pi integral from 0 to 2, and then x, there's an extra x is for the radius, and then times the function, which again was 2x squared minus x cubed dx. And it's a nice little integral, right? That's a very friendly integral. You can easily do that. Sometimes that x helps if I want to do e to the x squared function, and I want to rotate that. Oh, right, so I get that extra x for my du substitution, because that x is good sometimes. Yeah. Okay, that's definitely died now, and I mean I'm done. So whatever this is, that equals a number, right? You can integrate that. It's a simple integral. You distribute and go forward. And I'll post the homework soon, and yeah.